Now, one of the implications of all of this is we can interrelate stuff and rearrange things and solve for the density of a gas. All right, so the density for a gas is going to be directly proportional to its molar mass. This should make sense. A larger molar mass should give us a larger density. Because when we look at our density of a gas, densities are very low, but they are in terms of grams per liter. Density is also inversely proportional to temperature because as the temperature raises, the gas particles move further apart, and so they're less dense. All right, so let's take a look at how we rearrange all this stuff. All right, so density is mass over volume, okay? In this case, it's grams per liter. Mass is I take the number of moles and I use that molar mass. So I can take X moles times Y grams per mole, okay? And that gives me grams, right? Okay, we've got our PV equals nRT. All right, I can rearrange things. I can get moles over volume, not quite mass over volume, but it's getting closer to what that needs to look like. So if I take that molar mass and I multiply both sides by the molar mass, some stuff cancels out, and we end up with density is equal to the molar mass times the pressure over RT. Okay, it works out really nicely. Okay, so we're going to try calculating the density of carbon dioxide. So carbon dioxide is CO2, and it has a molar mass of 44.01 grams per mole. Okay, so at STP. All right, so our density, again, is our molar mass times our pressure over our R times our temperature, okay? So we're going to take our 44.01 grams per mole times STP, so 1.0 atmospheres. All right, so we need our 0.08206 liter atmosphere mole Kelvin, and our temperature 273.15 Kelvin. Okay, so Kelvin cancels, moles cancel, atmospheres cancel, and look what we're left with, grams per liter, right? And we will get 1.96 grams per liter, okay? All right, so now this bottom one, I want you to try this one. So in this case, molar mass is the same, R is the same, pressure is even the same because ordinary room conditions should be at 1 atmosphere. But now we have room condition temperature, so 20 degrees Celsius. So the temperature has gone up. So I want you to try this. Plug this all in, make sure temperature's in the right units, okay? And see if you can get the density of our carbon dioxide at ordinary room temperatures. Okay, if you did it correctly, you should have gotten 1.83 grams per liter. This makes sense. The density, again, is inversely proportional to temperature. The temperature went up. My gas particles started moving further apart, so my density went down. Okay? All right, and then we can take a look at this. Okay, we can figure out how many moles our gaseous arsine occupies at STP. This is just a reminder of that molar volume. Okay, remember this is molar volume. All right, and what you're going to get is 0.00179 moles. Okay, so to get the density, there's two things you can do here. Okay, if you totally spazzed and forgot what the rearrangement was to get the density of a gas, you could do moles to grams, okay, and then do your grams over your 0.4 liters, and that would give you your grams per liter. If you remember the formula though, then you can just plug the whole thing in. You need the molar mass for either of these, and it's 77.9 0.456 grams per mole. I know the formula, so I'm just going to do it this way. Save myself an extra calculation. Okay, we're still at STP, so we have 1 atmosphere. We get 273.15 Kelvin. We're going to get 3.48 grams per liter. Okay, and so that's how we deal with density.